Nehoma, everybody. Welcome back. It is Wednesday. Love it. Let's continue on. What were we talking about yesterday? Continuity, right? Okay, 3 types of discontinuities, but we only looked at 2 of them. What is this one that I'm showing with my hands? I'll draw it on the board. So that if what? See, here's the weird thing. I can't undo that. I don't know. My computer, every once in a while, just does this wonky thing. I can erase it, but I can't undo that line for whatever reason. Okay, I'm going to show a discontinuity without a lot of graph going on. What sort of discontinuity do we have? It is non-removable. Can you be more specific? It jumps. Okay, what about this one? Is it continuous anymore? No. What kind of discontinuity is this? Removable. We didn't talk about it, but I mentioned it. What about this one? Asymptote. Where do they go? Both of them are approaching what? I would call this an infinite discontinuity, but we didn't write it down. Cool. Nothing crazy going on there. The last problem that we did was an AP problem where we had to find a value that made it continuous. As we look over this problem, does it feel okay from yesterday? Any big burning questions that are left? Okay, cool. So here we go. We did that problem. Gosh, this is kind of interesting. It's almost like I picked a bell ringer that was going to fit this lesson like well. Let's do another example. I want to know, and I guess I should have just called this B, yeah? Last thing we wrote was an example? All right. Oh, we didn't name it A and B, so we'll just roll with this. I want to know for the following is f of x equal to the square root of 4 minus x squared. Is this thing continuous on this interval, the closed interval from -2 to 2? Now, there's a little extension from the bell ringer. I want to know if it's continuous from -2 to 2. I'm not asking you at a single point, right? So how would we even think about beginning this problem? I'm going to give you guys like 30 seconds. I want you to chat with one another. I'm okay with bad answers. There's no such thing as a bad answer. I mean, there are, but if you give me some mathy answer, it's good. How would you even start thinking about an entire interval rather than just a point? Unless you guys really have enough time to check every point between -2 and 2. Okay, talk it out. Ideas, some sort. What would you do?
They talked about something about the coordinates. Yeah, -2 on their second line over. That's just if it's close or open, right? It depends what bracket it is. That's what I heard from yesterday.
All right, here we are. Much broader question, yeah? Thoughts? Okay. Where are you expecting some wonky stuff to happen? Like, why would wonky stuff happen in this problem? What makes this function harder than one we did on the bell ringer? Just as a reminder, here's my bell ringer. The radicand was linear here, yeah? What's the radicand on this one? Oh, it's 4 minus x squared, right? It's quadratic, not exponential. X would be up there if it were exponential, Sean, just to be clear. Well, do you guys want to check all infinitely many points? Yeah, me neither. Can we pick some number in there, and we won't even pick an actual number. We'll just say, let this be a number in here. When we take limits, typically we use as x approaches what? C. So let's just pick it. I'm going to go ahead and say, hey, let's let C be in this interval, and we're only going to do -2 to 2. And I'm fine with that. Let's let C be any number between here, and then we're going to have to think about these numbers. That's a lot of numbers. That is not an ordered pair. What does this symbol mean? In the set of, and this is not an ordered pair, it's a what? It's an interval. I'm going to write that just in case anybody struggles. I don't like interval notation only because it looks like this ordered pair. Okay, so let's check here. If I want to know if this thing breaks anywhere, like if it was broken, undefined, that would be an issue. Do we all agree with that? So let's find the domain of this real quick. And it's going to be essentially the same as we did before. Anybody remember how to do nonlinear inequalities? Okay, we're going to review it because we did it last year. That's like maybe once or twice, 2 days, really short lesson. When we're looking at these, if I want to think about a parabola, and I'm actually going to graph this, 4 minus x squared. And I'm not going to make you guys graph it by hand or anything like that, but could you graph it by hand? If we had x squared and we added plus 4, what does that do to the graph? So let's check. Desmos, not YouTube. So if we have x squared, eventually, here we go, y equals x squared. Here's x squared. Cool with that? Okay, so if I do plus 4 right here, it's to the right. What if I wanted it to move left and right? Where would I have to put the plus or minus stuff? Inside the square. And anywhere there's an x, I'd put the plus or minus, whatever it is. Okay, so it was 4 minus x squared though, right? What is a minus x squared going to look like? You can say it. I didn't hear you. I'm sorry. Yeah. Yeah. Oh, your computer. Got it. Cool. What's negative x squared do? So this is negative x squared. If I add 4 to it now, outside of the parentheses, what's it going to do? Up. Okay. If I'm trying to take the square root of this, is there a place on this graph where it's truly positive? Okay. Is it here? So I'm getting a lot of blank questions. Is the y value, the actual value of my function right here? Like, I know that it's at x equals negative 3 right here, yeah? But what's the value of the function right here, roughly? Is it positive? So it's not positive. I can't take the square root of it. Can't take it. Everything in here is cool though, right? Now, we can see it on the graph when we have it in front of us, and that's all fine and dandy. What if I didn't have the graph? Where do I change from being positive to negative on a function? What do we call these? The zeros, the roots, the solutions, the x-intercepts, right? How do you find zeros or roots or solutions or x-intercepts? You use the F word, right? We just factor it. So I'm going to approach this much more engaged than, like we'll use this later for sure, but I want to remind us. I know that functions can change positive to negative at the x-intercept. It's the only place it can happen. Anybody who's like thinking, oh yeah, we kind of talked about it, the word multiplicity showed up during this conversation. So if you remember the word multiplicity from last year, the number of times a zero shows up, then you have at least a vague recollection of doing these things. So here we go. I want you to find me the zeros. And you do not have to annotate everything like I do, but I'm going to say a function changes sign. And it might change. I'm not going to write all that. At zeros. Roots, intercepts, whatever you want. This is like my driving motivation to this, which means let's just find the zeros. If I'm only looking at the radicand, because it's going to be ugly here for a second, can you find me the zeros of this? Lots of answers. I'm going to change this style. Find me the zeros of this. I don't care which approach you take. Find me the roots. I'm going to give you guys like 60 seconds, and we'll come back together. So I'm going to do, gosh, it's a difference, right? Do I know the square root of both? 2 minus x and 2 plus x? 2 plus x equals 0, which means if I wanted to find an x that makes this 0, we would get what? Negative 2 on this one and positive 2 on the other. Okay, if anybody's looking at this going, I didn't factor that, that's dumb. Just so you can see, if I add an x squared, I get this. How do you undo a square? Almost did the thing I do. Okay, square root of x, I got it. X squared, I'm sorry, what's the square root of 4? Love it, Rafa. Plus or minus 2, we get the same answers. Okay, so why do we find the zeros just now? What do we say can happen at the zeros? Oh, the sign change. Now, this is taking a little bit longer because I want to make sure we can do it without the graph. right? We're just reviewing some of the algebra skills. I'm going to put these things on a number line. That's it. Now, this is all just to find the inequality. It's a nonlinear inequality. It's a little bit more involved than the one that we've done in the bell ringer. I only care about two numbers on here. -2 and 2. Okay. Leanne and Aisha, not to... Do you guys remember the word multiplicity? Does that ring a bell at all? Okay, can somebody... Everybody else, I imagine you remember the word. Anybody remember what it is? I might have whispered it. Yeah, the amount of times a particular zero shows up or a factor shows up. Okay, each of these zeros, the roots, they showed up exactly one time. If an odd multiplicity occurs, why would I even talk about all this? If it shows up one time or 3 times or 5 times, the function does something. It crosses the x-axis. What if it shows up twice or 4 times or 6 times? It touches the axis and it turns back around. So there would be no sign change. Now, I'm covering all this again just to show this. I'm going to look at these things. Pick a number in any interval. Easiest number, preferably. 0 is a good choice. Let's plug it in. 4 minus 0, is that positive or negative? Don't even care about the number. It's positive. It means everywhere between, like we saw in the graph, it was above the x-axis. Using that multiplicity trick, without even needing to check, if it was positive here, and this was a root that showed up an odd number of times, what would I guarantee it is? Negative. Now, I'm just going to confirm that. Pick anything between 2 and infinity. Great choice. 4 minus 9 is negative, right? Same thing, multiplicity. Without plugging in the check, it's negative here. The reason that we've done this is we've just confirmed, is there anywhere between -2 and 2 that my function is broken? And by that, because there's a lot going on here, it's always positive. And can I always take square root of a positive number? So we just verify that, okay, there's nothing broken in between. And we've done it in a really rigorous and analytical way. Where there's issue with this, if I want to know if it's continuous, what do these symbols mean? They're closed. We just showed that it was continuous here just now. But we have to worry about these endpoints as well. Now, continuity at the endpoint gets kind of weird. Because when you think about continuous, you want to come from both sides. Can I come from the left of -2 though? My function just doesn't exist anywhere over there. So it doesn't make sense to do that. This whole little piece that we just did, first conclusion, therefore, continuous, on which interval did we just show it works on? -2 to 2, and here's the most important question. What symbols go on the outside of here? Did we actually check -2 and 2, or did we just check the inside? Inside. So what symbol? Parenthesis. Brackets if we actually checked them. So right now we have continuous everywhere in the middle. There's only 2 other places I need to worry about. Where would it be? -2 and 2. And I know that because we found it, what's the value that I should get out of f of x when I plug in -2? It's a 0, right? We already found that. So let's just verify that as we approach -2 and 2, we're good. Okay, I'm out of space down here, but we don't have a ton of room. I want to take the limit as x approaches -2, and based on what we see here, what direction do I have to come from? The positive. I have to come from the right, because I can't come from the left. My function doesn't exist there. Cool. Positive of f. And let's just see, we'll see what this is here in a second. And I want to check the limit as x approaches +2. From which side? From the left of that same function f. Now, whether you're doing a left or a right limit, in this one it's not going to be a huge issue. We don't have to change functions. What's the first thing we're always going to try with the limit? Direct sub. If I plug in a 2 as I come from the left, and -2, I'm sorry, what's 4 minus -2 squared? 0. Did you say something different, Rafa? Okay. What about as I approach +2? 4 minus 2 squared. Notice I already wrote that it was equal on both sides because I knew that this was coming. So we've showed never broken in the middle and it's defined at both sides. Is it continuous, including -2 and going all the way to 2? Boom. This thing right here says it's continuous at -2 and 2. Therefore, we conclude that f of x, not the function, it, you'd literally write f of x, like be specific, is continuous on, which interval did we just verify? Negative 2, 2, and most important part, brackets we checked. The parentheses was checked right here. The brackets was when we did these limits at the very ends. So we see closed on both sides. It's continuous the whole way through. Cool. Conceptually, it's a big problem. This is the hardest part, which you will likely be given a graph most of the time, but I want to make sure that we have this locked in for later as well. Okay, doable? Okay. Let's see here. Hey, this is like a very similar problem. Sweet. Okay. Before we move on, I should have asked any questions about that last problem that we worked. Should we do another nonlinear inequality, you think? Okay, so here we go. We're going to sneak in a definition, and it's kind of ugly for a second. But definition is continuity on a domain. Continuity on a domain. Cool. It seems so silly to write this, but we need it. F is continuous on its domain. So here we go. F, some function, is continuous on its domain if F is continuous. And I'm going to ask you guys to remind me, what's the symbol? Okay, if we don't know it, this one's going to show up a lot. We will use this one regularly. This symbol right here, it means for all. This is not a Holloway shorthand. This is an accepted math and logic shorthand. For all is an upside down capital A. We're going to use the heck out of it. I'm going to say a function is continuous on its entire domain if F is continuous for all C values that are in the domain. And I know that this feels roundabout, but we're going to use this right away. Okay. The function, we say the whole function is continuous somewhere if for every value of C it's continuous, which you don't have time to check infinity, so we might have to do some fancy workarounds like we did in the previous. So here we go. I want to know, example, is the function defined as f of x equals the square root of x squared times x minus 1. I want to know, is this function continuous on its domain? Cool. Now, this question feels different than the previous example, I think. But notice it's the same question with one little step added. On the previous question I asked, was it continuous from -2 to 2, right? Which just happened to be exactly the domain of that function that we found. We're doing the same thing, except I'm not giving you the domain. Now, if we're trying to take the domain, just like last time, I need the square root, the radicand, the inside piece, to be what if I'm taking it square root? To take the square root of a number, the radicand must be greater than or equal to something. 0. Can you guys tell me the zeros of this function here? So you've given me 2, Rafa, and I'm okay with that. Could you say more than 2? Rafa said the zeros are 0 and 2. Sorry, 0 and 1, which I agree with. Is there another one that we could add in there that's also included, though? It's 0, 0, and 2. Why? Because x squared is x times x, right? That's a multiplicity idea. So let's knock this out real quick. As we look at it, what are the zeros of that inside radicand piece? X equals 0, 0, and 1. Before we move on, somebody in here probably, I don't know who, somebody does not quite get where we got all these numbers from. Now's your chance to ask. Good point, Sean. How did you get these numbers? Okay. Can you be more specific? The radicaned. So this is what we start with, right? And then I just say, oh, what value of x makes this 0? And that's a silly question every time. It's 0. What value of x makes this 0? 1. This one had 2 of them. I listed it twice. Okay, just to make sure we're all there. Gosh, what do I do with those zeros? What do we do on the previous problem? I put them somewhere. I put them on a number line. I want you guys to do the whole number line thing. Find me where it's positive if we actually take the domain. Cool. I'm going to give you guys a second. I'm going to walk around and be nosy. As we're looking at this, I'm going to construct this wonderful number line. 0 and 1. And then remember, this multiplicity was what? 2. This one was 1. So I know that sign changes. Sign doesn't change. Cool. This is the easiest interval. Let's pick a, I don't know, number between 1 and infinity. 2. I'm going to plug it in and see what happens. 2 squared is a positive times a positive. Because 2 minus 1 is still positive. Don't care about the number. I only care about the sign. What's a positive times a positive? Positive. Multiplicity. This showed up an odd number of times. Means we switch signs. If it was positive here, when I cross that 0, now I'm what? Negative. This number had a multiplicity of 2, which is even, which means we don't change signs. If it was negative here, what is it on this side? Negative. Everybody have these positive and negative somewhere. We're going to add one little piece to our number line. Little tiny. This is just the radicand that we're focusing on, right? So we're going to go one step further. I need you guys to get in the habit of labeling when we do this. I want to check what does it do to f of x. So I've done the radicand inside. Like I've just done the number line with the radicand. And let's just see. Can I take the square root nicely of a negative number right here from negative infinity to 0? So it would just not be defined, right? Undefined. And really we should write undefined, but I'm okay with using this. From 0 to 1, can I take the square root of it? Undefined. Can I take the square root of it from 1 and higher? Yes. Now, we have to be really careful. This thing has an interesting domain. Can you tell me the domain of f from this picture? Where is it defined and where is it not defined? I'm going to make a smiley face here. Greater than 1. Anywhere else that I can plug it in? Greater than or equal to or greater than 1? Or equal to, because it'd be positive and 0 is fine. Anywhere else that I could take a square root of it? 0. So that means we're going to write the domain real quick, because if we're wondering is it continuous on its domain, we better be able to say what the domain is. Do you guys, I don't care which one we go with, let's find the domain of f real quick. And not find it, because we've already done the hard part. Let's write it. Prefer set builder or interval? Okay, I'm going to give you a domain in 2 different ways, and we'll see which one we like. I like set builder. The domain of this is a set of all x such that either x is equal to 0, here, that's okay, or x is greater than or equal to what number? 1. Can what? Formally, I'm apprehensive to say yes. I don't care personally. More commonly, you would use or with a symbol. I would just write the word or rather than trying to just differentiate between these symbols. Okay, this is set builder. Alternatively, we could say x is in. This one's weird, right? This is not an interval. So we just say, okay, well, it's either in just 0 or it's in 1 to infinity. These 2 statements, same. These are synonyms of each other. They're just different styles. Set builder, interval. Which one do you guys prefer? That is awesome. Me too. Most people prefer interval. Okay, so we're going to just commit to set builder for the next couple examples. Okay, so there's a whole domain. And then we have a weird kind of question to think about. Is it continuous on its entire domain? Why? Where's the weird little part? So it does jump, right? We have a huge discontinuity between 0 and 1. Now, even in that situation, great catch, there's a weirder part that, for me, contextually, that I think of. If you talk about continuity at a single point, which we did yesterday, you have to have the limit from the left be the same as the right, and it has to be defined there. Look at 0. Can we even think about trying to take the limit from the left or the right? Because my whole function is not defined there, right? So, what do we conclude? It is discontinuous on its entire domain. So I'm just going to say disco on entire domain. And then we wouldn't have to go any further, but we're going to take one step further just to build the conceptual part of this. But continuous if we restrict, or if it's restricted, to what values of x could we actually say it's continuous for this whole place? So 0 would work, but remember, we can't talk about continuity here if we can't come from the left and right. But there is a whole section where things are cool, or smiley. It's greater than or equal to 0. So if we restrict this to x such that x is, greater than or equal to 1. I misspoke. I'm using the 1. Boom. And we have it. Cool. This problem went a little bit further, but how's it feel? Okay, I'm going to hook you guys up tonight. We're not going to have homework this evening. I would, but I didn't write down what the assignment would have been. So be prepared for the AP problems tomorrow. Before we're done, we still got 3 minutes, right? Okay. Hands up real quick. I'm not asking specifics. Who found something that we did today that you weren't 100% confident in your ability to do? Cool. I want you to jot down in your bell ringer underneath anything that you struggled with today. Be as specific as possible. If it was everything, bummer. I do study hall today, but don't write everything. Say finding the domain of a function or finding the zeros, whatever specific part you found most difficult. Cool. Once you have that jotted down, we're just going to chill for a minute because we're at like a natural spot to pause.